Okay, so now in this video we're going to look at centripetal force. Okay, so basically the way to think of it is anytime you have an acceleration, you have an associated force. So any force or combination of forces can cause a centripetal acceleration. So this is very important. One thing to note is that the centripetal force, which we're about to talk about, is not a set force like friction or weight. Okay, it is what causes the centripetal or circular motion. So any net force that causes UCM or uniform circular motion, we call it centripetal force. Right? So this is not one of those forces that you draw on your free body diagram. This is one of those forces that is your net force, right? So again, you see that word centripetal. So that means that it is directed towards the center of the circle, okay, which means it's along the same direction as the centripetal acceleration. So this centripetal force formula, right, so how do we calculate force? Just mass times acceleration. And so you're going to see a lot of times they'll do F sub c is equal to m times ac. But what you can do is you can substitute in the two equations for ac, right? So you get mv squared over r, or you get m omega squared r. Okay, so you can do that because a lot of times what they'll do is like how fast can it go around the circle if it's experiencing this much force, right? What is the angular velocity, right? What is the radius of the turn? Okay, so one thing to remember, I just said it, right? Fc, or centripetal force, represents a net force. And let me highlight that. Okay, so one thing to note, it is not like friction, it is not like normal force. It's the sum of all those forces acting together. So what we do is we don't draw it directly on our free body diagram. We can put it near our actual free body diagram, but we don't draw it on our free body diagram. Okay, and so our problem solving strategy for forces comes into play, right? So since it is a force, we're going to have to follow our steps of draw, sum, solve. Right? So draw the free body diagram, sum the forces. Now, when we sum the forces here, we're not going to do it x and y. We're going to do what I call circular, non-circular. But I will tell you this, very much it looks like the circular direction is our x direction and our non-circular is our y direction. And you'll see here in a second, I got a little card drawn off to the right. We'll do a quick little free body diagram to show you how this works. And then the final step, again, solve for what you're looking for. Right? So just simply solve, right, for what you are looking for. Right? The same exact steps that we did way back in Unit 2 come back here in Unit 5. Alright, so if I want to do a quick little free body diagram of this car taking a turn, because it's a lot of situations will be cars taking turns. So what that means is I take a car around a turn. The turn itself, right, has a radius, and the cars are going to try to navigate this turn with a velocity. Okay, and so that produces the centripetal force, it produces the centripetal acceleration. But in actuality, when you get these situations, what is actually causing that force, or that centripetal force, right? So I've got my non-circular forces. Because this is a surface, we still have, right, or we're on Earth, we still have the weight, and because of the surface, we still have a normal force. But now it's the next thing that you draw on this is what you is where you go, okay, what kind of force am I really looking at here? Okay, and so what you do is, if I'm trying to prevent it from going to the outside, my friction points to the inside. If I'm trying to prevent it from going to the inside, my friction goes outside. Interestingly enough, this is almost the same exact point, right? The same speed. But this is what happens when if I'm traveling in a circle and I lose speed, I go into the turn, and if I go a little too fast for that turn, I go outside of the turn. Okay, this is how they can predict, if satellites are going to crash into Earth. They can see that they're in circular orbit, which we'll get into later in a couple videos. But the second it drops to a certain speed, they know it's going to start coming spiraling inward because it doesn't have enough speed to be at that height. Okay, but let's look at it in terms of a car, right? And so here we got A, calculate the centripetal force on a 900 kilogram car that negotiates a 500-meter radius curve at 25 meters per second. And then static friction prevents the car from slipping. Okay, what is the minimum coefficient of static friction between the tires and the road? Okay, so let's look at part A, right? So part A, we're just going to use our basic M sub C equals MAC. And because we have a linear speed, right, that's the 25 meters per second, we're going to use mv squared over r. And so we're just going to plug in numbers. So we're going to do m, 900 kilograms, times v squared, times 25 squared, over 500. Now, you should recognize this, this 25 squared over 500. That was the centripetal acceleration from the last video in one of the examples. So we could have just as easily as said, okay, I recognize that's what it is. I can just multiply what I got in the previous video times 900. But this is using the full formula. And so you're going to find that you get 900 times 25 squared divided by 500. Okay, it would help if I hit the division symbol. And you're going to get that it is a centripetal force of 1,125 newtons. Okay, now I'll show you two ways that you can do this second part. Okay, so part B, right? So it's like B1, B2. Okay, so B1 involves our steps of draw, sum, solve. So you can see I have the free body diagram up there to the top right, okay, where my car is. And so I'm going to sort this into circular and non-circular, right? In unit 2 we did X and Y. Okay, so one thing I didn't draw on my free body diagram hammer or indicate is that if I'm taking a turn, right, I know my centripetal acceleration is going to be inward, right? My centripetal force is going to be inward, and I would actually be doing this this version, okay? So I know I would be going with a negative acceleration, right? Because I want to avoid slipping in, okay? And so now when I sum the forces, right, my non-circular is very much like what it would be an object sliding on a surface, right? And so it's going to be the sum of the forces is equal to 0, right? We're not accelerating up or down. And so I have normal minus weight equals 0. And so my normal, just like usual, equals my weight. And now when I go over to my circular side, the sum of my forces is going to equal MAC, right? And I'm going to do the sum of the forces is equal, or let me get rid of that sum because we can just start plugging in, right? And so the sum of my forces is going to be friction is equal to MAC. But remember, friction is mu Fn, so mu Fn equals MAC. But we found Fn to be mg, but we also know that AC is v squared over r. And so if I do a little bit of algebra here, the mass, right, same car, so it's a mu g equals v squared over r. And if you recognize this right here, right, that is the acceleration of a sliding object. Because guess what? Whenever the car is trying to slip or skid, it's now a sliding object. Okay? So this version of the equation, right here, is kind of the base. So what I can do now is really solve this for anything that I want. And so I'm going to solve this for mu. So mu is going to be v squared over gr. And so now I can just plug it in. So I'm going to do 25 squared over 10 times 500. All right, I'm going to round to 10 for my acceleration due to gravity. So 500 times 10, and so I get a coefficient of friction of 0.125. Okay, so that is the coefficient of friction between the tires and the road. Now, like I said, that's one way to do it. That's kind of a long way if you want. But again, this right here, I'm gonna put it, put these arrows pointing at it. That's very important. If you can memorize that relationship, now you can solve for anything. For example, how fast can I take this turn? So I would say V equals the square root of R mu G. Right? And so that's how I would find, how fast can I take this turn without slipping. Okay? And now the second way you can do it is knowing that Fc is the net force, and knowing that the only force is friction. Oh, not normal force. So knowing that the only force that is acting here on the car, right, is friction, I can say that friction equals Fc. And so I have the answer to part A. I would just need to do, again, I would need to know, right, the normal force. So it's just mu mg. And so what I'm going to do is I'm going to solve mu is equal to Fc over mg. So it'd be 1125 over 900 times 10. And you should get the same answer of 0.125. And lo and behold, I do. So the coefficient of friction, you see I solved it two ways. One using my circular, non-circular way, but then I also solved it just using simply knowing that it's the friction that's causing the net force. Okay. Now this turn was flat. Okay. But what happens when we introduce a banking, right? So a banked curve. This is like the next evolution of the problem. So a banked curve is one curve when the slope of the road helps you negotiate the turn. The greater the angle of banking, the faster you can take the turn. Okay, so for example, if you ever watch NASCAR, most of the tracks, I can think of two off the top of my head, Martinsville in Virginia, Loudon International Speedway in New Hampshire, are flat tracks, so they'd be like the previous question. Okay, but the majority of NASCAR tracks have some sort of banking to them, right? So the way you think of a banking, right, it's very similar to our Unit 2, right, inclined planes. So it's essentially an inclined plane that you're taking a turn on, okay? Now, an ideal bank turn is one in which you can take the turn, or an ideal bank curve, is one in which the angle allows you to negotiate the curve at a certain speed without the aid of friction between the tires and the road. Okay, again, ideal bank curve versus bank curve. Bank curve, there's probably friction. If there's no friction, then that banked curve becomes an ideal banked curve. So in this example, the net external force is going to equal the horizontal centripetal force in the absence of friction. Okay, and so if I do the free body diagram, it looks very similar to if we were on an incline. So we would have the normal force, right? We still have surface, okay, and because we're looking at if it was frictionless, we would have the weight down. But here's the trick to this problem. The centripetal force and acceleration is actually horizontal. So AC and FC are actually horizontal, right? So it's into the circle, right? And so what you think about is, what is the force that is actually creating this circular motion? Well, it's going to be the x component of our normal force, okay? But again, this will come into play. The y component of your normal force will come into play. And so that you can break those two, or you can break the normal force up, right? Because what we're really doing is our coordinate system goes plus y plus x is normal. Okay, it's our traditional, versus when we did inclined planes. In fact, this would not be pointing to the right. This would actually be pointing to the left, especially if I'm trying to navigate the turn, right, in that direction. okay, which is how I have it set up. Okay, and so Fnx would be Fn sine theta, right? Because what happens is this is the angle you know, right? That's the angle of incline, and Fny would be cosine. Okay, and so if I do my summing of the forces, so I'm going to do circular and non-circular. Again, I do sum of the forces in the y, or the sum of the forces in the non-circular. So let's think about it that way. So the sum of the forces non-circular equals 0. And so I would have Fny minus Fg equals 0. And note that Fg goes straight down. And so I would have Fny equals Fg. So that would be Fn cosine theta equals mg, which means Fn equals mg over cosine theta. Okay. Now when I go into the circular direction, the sum of the forces centripetally, or circular, is MAC. And the only force acting, because this is an ideal bent curve, would be Fnx. So the normal force is x component, so that would be Fn sine theta equals max. But I have an equation, or I have a relationship for Fn, so I'm going to take that and plug it in there. And when I do that, now I have mg over cosine theta times sine theta equals ma. And I put an x there. These should be c's. Sorry. Right? Everybody wants to make it the x direction. Okay. So I can do a little bit of algebra here. Right? The m's are going to cancel out. Sine over cosine is just tangent, so I'm going to get g tan theta equals AC. Right? So again, here's where we're kind of looking at some of these relationships. But remember, AC is v squared over r. And if you remember, this right here is the acceleration down an incline. Right? In the absence of friction. Right? If we have friction, then we got all this other stuff happening. Okay? So this is actually looking for what is the speed that we can take this at. So I'm going to solve this for v, and I'm going to get the square root of rg tan theta. Okay, and so now I can just plug in, right? Or sorry, it tells me to find the. Sorry, I didn't read the question, but it tells me first to find the equation, right, or derive an expression for the speed, and then it says, okay, to illustrate this, calculate the speed of a 100 meter, at which a 100 meter radius curve banked at 65 degrees should be driven if the road is frictionless. All right, so I didn't read the question; I just jumped right in, and so we're going to do our r, right, times 10, so 100 times 10 times tangent of 65. So again, make sure your calculator is in degrees, not radians. So 100 times 10 times tangent 65. And I'm going to get a speed of approximately 46 meters per second, which if I do a conversion factor is approximately 103 miles per hour. Okay, so that would be my speed to navigate this on its own. Okay, so if you want to go a little bit further, you can now introduce friction into this by making it just a banked curve, where the expression gets very complicated because you got to address that friction problem. Okay. Now we're kind of done talking about a little bit of the rotational motion. Now we're going to kind of put a little effort into Newton's laws of universal gravitation and Kepler's laws of planetary motion.